Friedel-Crafts alkylation. It is an electrophilic substitution reaction given by benzene, through which alkyl benzenes or homologues of benzenes can be synthesized. As an example, when benzene is treated with methyl chloride or chloromethane in presence of anhydrous aluminium chloride, one of the ring hydrogen atom is replaced by CH3 group to form toluene. This reaction is an example for Friedel-Crafts alkylation. This type of compounds are called alkyl benzenes or higher homologues of benzene. This reaction is carried out in presence of Lewis acid catalyst like anhydrous aluminium chloride. It promotes the dissociation of methyl chloride into methyl carbocation. Methyl carbocation is the electrophile in this reaction. Mechanism. It is an electrophilic substitution reaction, hence it involves 3 steps. First step is generation of electrophile. Here the electrophile is CH3 plus or methyl carbocation. It is generated from methyl chloride through heterolysis of carbon-chlorine bond. It is promoted by Lewis acid catalyst AlCl3, which can accept chloride ion. So it can be represented like this: CH3 plus methyl carbocation plus AlCl4 minus. Then second step is formation of sigma complex or arenium ion. When methyl carbocation approaches one of the ring carbon atom, say first carbon atom make a sigma bond with a positively charged carbon of methyl carbocation to form a resonance stabilized intermediate carbocation. It is called a sigma complex. These pi electrons are used to make this sigma bond. It is stable due to resonance. 2 more resonating structures can be drawn. Shifting of a pi electron changes the position of a positive charge in the ring. So these are the 3 resonating structures. Structure 1, 2, 3. It is a structure of a sigma complex or a resonance stabilized carbocation intermediate. Step 3 is deprotonation. In this step, sigma complex loses H plus ion to form final product toluene. This AlCl4 minus abstract hydrogen atom from sigma complex as a proton. the sigma electrons of CH bond is shifted to benzene ring, giving AlCl3 regenerated catalyst HCl and toluene. In Pridelkrav's alkylation reaction, the electrophile is a carbocation. Carbocations have a unique ability to undergo rearrangement through 1,2-hydride shift. Hence, rearrangements are possible in Pridelkrav's alkylation. For example, when benzene is treated with normal propyl chloride, in presence of anhydrous aluminium chloride, the major product obtained is isopropyl benzene. Normal propyl chloride is 1-chloropropane. In this reaction, the initial carbocation, that is electrophile, generated from propyl chloride is a primary carbocation, and it is rearranged to secondary isopropyl carbocation through 1,2-hydride shift. This secondary carbocation is more stable, and hence this type of rearrangements are energetically favorable. This new carbocation will be acting as a electrophile in the second step. That is, a sigma complex is formed by accepting pair of electron from one of the ring carbon atom by isopropyl carbocation, and hence the final product will be isopropyl benzene. Carbocations are classified into primary, secondary, tertiary depending upon the nature of a carbon atom carrying positive charge. The relative stability of carbocation follows. Primary is least stable. Secondary is more stable than primary, and tertiary is most stable among alkyl carbocations. So carbocations have a unique ability to undergo rearrangement in which a less stable carbocation is converted into more stable carbocation. Another example for rearrangement of carbocation is this one. It is isobutyl carbocation. It is a primary carbocation. When it is formed as an intermediate in an organic reaction, it undergoes a rearrangement through 1,2-hydride shift. That is, one of the hydrogen atom is shifted from first carbon to second carbon in the form of H- ion. So that the central carbon atom have only 3 electrons, and hence it carries a positive charge. It is called a tertiary butyl carbocation. It is a tertiary, more stable than primary. So if benzene is subjected to Pridelkrav's alkylation using isobutyl chloride, the major product obtained will be tertiary butyl benzene. Initially, isobutyl carbocation is generated from a mixture of isobutyl chloride and anhydrous aluminium chloride. The isobutyl carbocation then undergoes a rearrangement through 1,2-hydride shift, and tertiary butyl carbocation is formed. This tertiary butyl carbocation interact with the benzene ring to form sigma complex, which ultimately lead to the formation of a tertiary butyl benzene.